So first question, the following questions are related to the elements of the second row in the periodic table. So note, this is in the second row. So what is in second row? So lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine and neon. Right, so identify the element that has the highest electronegativity. Discard the noble gas. So you know that fluorine is the highest electronegative atom in this period, as well as the periodic table, except if you neglect about the noble gases. So because we don't define the Linus Pauling scale for noble gases, so here this should be fluorine. And remember here what they said, write the symbol. So when they say write the symbol, don't write their names. Okay, so if you write like symbol and in within bracket if you write like fluorine, don't do that. Just do what they have asked. That's it. Identify the element that has an electrode which conducts electricity. So you typically know carbon from many different electrodes like graphite, diamond, carbon nanotubes, and C60 buckyballs. So these are different forms, electrodes of carbon. But at your level, normally we study about the carbon, diamond, and graphite, right? So you know graphite can conduct electricity. Okay, but diamond cannot. What would be the reason? So the reason is diamond, if you consider about the hybridization, in diamond, carbon is sp3, right? But in graphite, there are sp2 and sp3. So sp2, when it goes sp2, there is this unhybridized electron, so it can act as a parallel layer in between the layers, so there will be like a conduction of electron layers. So that is why it shows electricity, conductivity. In fact, identify the element that forms a monoatomic ion, largest in size. So you know in the periodic table, as we have discussed many times, so in general in the periodic table, atoms in the left-hand side across a period will have the largest radius. And when you go through in this side, so it will decrease, right? But on the other hand, these elements can form either cation or anion and get stabilized. For an example, lithium, there's a NS1 configuration which is not stable, so it will quickly go to lithium plus. And beryllium is stable because it has an S2 configuration. Then boron, carbon, nitrogen, oxygen, fluorine. So nitrogen, oxygen, fluorine, you know, F will be stabilized in F minus, O will be O2 minus, N will be N3 minus. Okay, so basically when you consider about the sizes, you know, for the positive ions, the sizes are smaller than its neutral element. For the negative ions, the sizes are larger than its neutral element. So basically, when you consider about nitrogen, oxygen, fluorine, it will decrease from nitrogen to oxygen to fluorine. But for its stable ions, it will be the other way around. Okay, so basically, N3 minus would have the largest radii, then it will be O2 minus, and it will be F minus. Okay, for an example here in this period. So this should be N3 minus. Why it is N3 minus at first point? Because it is stable. But normally you consider about F minus, it is not stable, right? So, I mean, alone it is not stable. It can quickly form F2. So those things can happen. Identify the element that has no p electrons, but has a stable S configuration. So there are only two elements which belongs to S block here, lithium and beryllium. But as I told you just before, beryllium has a NS2 configuration. So definitely it is a stable element. So this should be beryllium. Identify the element that has the highest first ionization energy. So typically, you know, the lowest first ionization energy will be for S block elements group 1, and the other way around, highest would be the noble gas in the top period, like the first period. So first or second, because you don't see the second. So hydrogen, helium, lithium to neon. So they're asking the elements in the second row. So it would be neon. Identify the element that forms the most electron deficient trigonal planar. So this is very, very, very common that we have learned in many cases. So we have to identify the Lewis acid here, right? So typically, you know, in our theory classes, we talk about BCl3 acting as a Lewis acid and NF3 acting as a Lewis base, where the lone pair in the nitrogen molecule atom can be given to boron. So NF3 gives the lone pair, so it's a Lewis base. BCl3 accepts, so it will form NF3 BCl3. Okay, so here in this period, so we have boron, which forms electron deficient compound. Why? When you consider about BCl3, you see around boron there are only 6 electrons. That is why it is electron deficient. To make it saturated, so you need to have 8 electrons. Okay, so 8 electrons, because second group maximum there will be 8 electrons, but here you have only 6, so that is an electron deficient compound. So boron forms electron deficient compounds, and at the same time you can see this is a trigonal planar structure, so there is only 3 bond pairs, no lone pairs. The shape is trigonal planar. Right, so moving on, so you have given a skeleton and you need to draw the most stable Lewis dot cross structures or dot stas structure. So again, this is very simple that you can draw because there are no charges in this molecule. So it will be very easy to draw by taking the lone pairs as well as the octet configuration. So there are 3 oxygens here. So 3 into 6 is 18, and sulfur also has 6 valence electrons, 24, and fluorine, 2 fluorine, there will be 7 valence electrons. So basically there will be 24 plus 14, which gives you 38. Okay, so 38 electrons should be there in this molecule. Okay, I mean the valence electrons. So if you divide this by 2, you will see there should be 19 electron pairs. Okay, I'm telling just the general way that how we draw the structures, if you remember. So 9 out of 19, 1, 2, 3, 4, 5 are gone. So there should be 14 electron pairs that we should put into this structure. But remember, normally we begin with the terminal atoms to complete their octet. So if I put like this, 3, I can put like this, 3. In the same way, you see here, how many? I have already put 3, 6, 9, 12. So 2 are remaining, that should be going to this middle oxygen. So everywhere octet is completed, right? However, so if you put here fluorine will not have charges because it is in group 7. Oxygen would have a negative charge here. And sulfur, you know, it is in group 6. So here there is only 2 bonds. So there will be 2 bonds less. Only 4 bonds here. So it should be 2 plus. Okay. So what is the easiest thing to minimize the charge? That is the next step. So minimize the charge. So you give this negative towards this sulfur and complete the bond. Now sulfur, remember, it is in the 3rd period, so it can form more than 4 bonds. Okay, so here sulfur would complete its octet and it will have more electrons. Okay, in fact, sulfur would have 6 bonds here. This is for fluorine, and this is for oxygen, the next one, and this is for fluorine. So show all the valence electrons. This one, this one. Okay, so these are dot dash, not dot cross. Okay, so this will be the structure, because now there is no charge here and no charge separation even like here, so it is complete. Okay, now these things are very straightforward, but I still take some time because to remind you something again. Okay, give me a second. Right, question number 2. So here it is again very same like the previous paper. They have given a LOE structure, and you have to draw unstable structure that can be drawn. So it is not hard. You just need to draw 2 of the unstable structures where you can put positive charge on oxygen and maybe another positive and negative with a big charge separation on nitrogen. So can be done. Okay, but don't forget oxygen is more electronegative than nitrogen, right? So if nitrogen has a negative charge, automatically it would be an unstable compound. Okay, so how can I draw that sort of a structure using this one, using this typical structure? So if I want to make oxygen a positive, so what I will do is I will put these 2 electrons, draw these 2 electrons towards this direction. So I can make a bond here, and 1, 2, 3, 4, 5. So 1 electron is missing, so that I can put a positive charge here. And then when I put this double bond here, what it will do is, sorry, here there will be more than 8 electrons. So that cannot be happen. Basically in a structure that cannot be happen. Okay, so in that case what I am going to do is I'm going to draw this bond towards this nitrogen, so making this nitrogen more electron negative now, and this oxygen a positive charge. So this would be one structure where this nitrogen is negatively charged and this oxygen is positively charged. Okay, that would be the one perfect structure that you are going to get. The next thing that I can do here is, instead of making this nitrogen a negative, I can make this nitrogen a negative. So see, there are 3 nitrogens available here. Okay, so you can make these bonds as you want. Either you make, first I make this oxygen positive and this nitrogen a negative. Now what you can do is you can do this nitrogen, make this nitrogen a negative charge. So basically what it will do is, if you, the next structure for an example, okay, so if you want to make this nitrogen a negative, what I can do here is take this double bond and apply that into the first nitrogen. Okay, so it will be like this. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so keep that in mind what I'm going to do here. So here is a negative charge, and here in nitrogen now there are 2 hydrogens here attached. These are hydrogens. Okay, so when you shift 2 electrons, you have to again think about this nitrogen as well, right? So this nitrogen, so here there will be a negative charge, so this nitrogen will be in the same way, but remember here there is an electron deficiency, so you cannot have that. So this lone pair around in this last nitrogen should be given like this to form the double bond. Then this nitrogen will become positive. Okay, so that is the most easiest way of drawing. You need to just shift the electron flow from one side to the other. Then you can draw easily two resonance structures which are not stable. Sorry for that. Now here, the important thing that you need to understand here is why they are unstable. So at first point, you need to mention here, you can see here, oxygen, which is the most electronegative, has a positive charge in this first structure. So it is not good. As well as when you compare with oxygen and nitrogen, oxygen is more electronegative than nitrogen. So having a negative charge on nitrogen is normally stable. But when you have oxygen in the molecule, then you have a nitrogen and nitrogen has a negative charge. So it is a problem. Okay. So think about those two factors. Okay, this is a very easy question again. Next one, you have given the Lewis structure. What you have to do is you have to put the pairs geometry, electron pair geometry and shape, then hybridization. These things are very simple now. Okay. So oxygen 1 is the oxygen that is bound to fluorine and nitrogen. So you see VSCPR pairs. So VSCPR pairs means, I think I have told you this before. This EPR pairs means you have to count the bond pairs plus lone pairs. So around oxygen here you have 2 bond pairs and 2 lone pairs. So here it should be 4. And in the same way, I will do for 1. In the same way, you can do for nitrogen, carbon, and nitrogen 4 very easily. Okay. So electron pair geometry, you get the bond pairs and lone pairs, and that means the total repulsion unit. And you consider the shape based on that. For an example here, there are 2 lone pairs and 2 bond pairs. So the total repulsion unit is bond pairs plus lone pairs. That is what we call VSCPR pairs. Then you need to get the shape based on that, the geometry based on that 4. So 4 is basically tetrahedral. Okay. So when you go to the shape, now you need to consider separately the bond pairs and lone pairs. So there are 2 bond pairs and 2 lone pairs. So you know this is angular or bent. And for the hybridization, I have told you many times before, you have to again take the sigma electrons. So here 1, 2, 3, 4. So basically there are 4 units. So there are 2 sigma bonds and 2 lone pairs. So you need to add all them. So it is basically 4 units, which makes this atom sp3. Okay. So nitrogen 2. So 3 here, 3 repulsion units here. So this should be trigonal planar with 3. And shape is again angular or bent or angular. So you can write anything, okay, both. And 1, 2, 3. So 3 sigma, 2 sigma bonds and 1 lone pair. So 3. So this should be sp2. And carbon 3 is this one. So 1, 2. So only 2 repulsion units. And electron pair geometry is linear. Here it's also linear, no lone pairs. And the hybridization is sp. And nitrogen 4 is this one. So again, 3 repulsion units, trigonal planar geometry. Here also trigonal planar geometry. And the hybridization is 1, 2, 3 sigma bonds. So sp2. Right? These are very straightforward things at this point because we have discussed 8 papers. Okay. Identify the atomic hybridized orbitals that is involved. So again, very similar. So when you consider about fluorine and oxygen, so oxygen here. So I will just consider about this structure and try to write down its hybridization. Okay. So fluorine, you see here, it is a terminal fluorine atom. So it could be either a 2p orbital or based on the repulsion units, it could be an sp3. Okay, so for terminals, always it could be very same. Okay, so don't forget that for terminals it can be same. In the same way for chlorine here, this could be now 3p, not 2p, because chlorine is below, or either again sp3. And all these others now you should know, because this is oxygen sp3 and nitrogen is sp2 and carbon, this is sp2 and carbon, wait, this mistake here. Okay, this is sp2 and carbon here, this is sp, as we have drawn here. Here this is again sp2 orbitals involved, and here it is sp3. Okay, so what is the thing that you have to understand here? So any sigma bond that is going to form, so here always remember you have to find the sigma bonds. That is what they have given, following sigma bonds. So when it forms the sigma bonds in between each of these atoms, all these orbitals going to participate. This one, this one, this one, this one, this one, this one, this one. Okay. So for an example, if you consider about the first one, fluorine and oxygen, so it should be either 2p3, 2p mix with O1, which is sp3. So you have to write all these things. Okay, but remember these are only for the sigma bonds. Sigma bonds. So don't forget that it's for sigma bonds. So what can you say about this double bond between carbon nitrogen and carbon nitrogen? So if you remember, when you have sp2 and sp, normally the double bonds that would form is between the unhybridized p orbital. Okay, so sp3, it is a saturated compounds, no double bonds. But when you go for sp2 and sp, there are double bonds. So these double bonds are formed because of the unhybridized 2p orbitals in carbon as well as in nitrogen. Okay, so don't forget that. Let's move on. So identify the atomic orbitals involved in the formation of the pi bonds. Now they have given the pi bonds section. So there are only two pi bonds here, carbon, nitrogen, between nitrogen 2 and carbon 3, and carbon 3 and nitrogen 4. So basically here all the answers should be 2p, right? So all these are 2p. How are the two double bonds oriented? So if you remember, when we discussed about the hybridization of carbons, when it forms the saturated and unsaturated compounds, we normally orient these bonds perpendicular to each other. So the answer here should be perpendicular to each other. So if I take a simple example, so when you have this ethylene compound with a double bond here, okay, so when you have this ethylene compound with a double bond, so basically what we draw here in the orbital diagram, like the orbitals, when you think about the orbital of this carbon and the rest, the carbon that is adjacent to it and forming the bond. So you know this is a sp2, so this is sp2, this is sp2, which I have drawn here. So there will be a sigma bond here, and don't forget the pi bonds are formed between the unhybridized p orbitals, right? Okay, so this is for a sp2 and sp2 mix. Okay, so if you have like a ethine compound like triple bond carbon, then don't forget the unhybridized p orbital in the adjacent carbons. So if this is a carbon, this is a carbon, it would form one bond to form the one pi bond. The other pi bond is formed another unhybridized p orbital, which is perpendicular to the first pi bond. Okay, that is what they are asking, how the two double bonds are oriented. So you have to tell the two double bonds are perpendicular to each other. Okay, Give an example of a molecule that has a similar orientation of bonds. So you have to find a molecule where there should be two double bonds and the atoms are not more than 3. So the simple molecule, for an example, is carbon dioxide. So carbon dioxide, there are two terminal oxygens here, and carbon, you see here, the hybridization is sp, which has two double bonds. So it would have a perpendicular two double bonds here. So, okay. Right, part C, an atomic orbital is described by the quantum numbers. So you know NL, ML, MS. So here they have given only the 3. Write the appropriate quantum numbers that and the name of the atomic orbital in the boxes given below. So basically, you need to fill the blanks. So here they have given the atomic orbitals and N, L, and M. So you have to find the principal energy level, all those things. So when you think about the atomic orbital, automatically you can find the principal energy level. Here this is 3p, so it belongs to the third energy level. So automatically this N becomes 3. And also this is a p electron, so automatically L becomes 1. In the same way here, this is a 2s electron, so the N would be 2 and the L will be 0 and ML also will be 0, because if L is 0 for S, ML also 0. So this is done. So what about this one? So this is N, so this should be surely should be a third energy level electron. So this should be something related to 3, and L is 2. So L is 2 means it's a D electron. So it should be 3D. Definitely it should be 3D. So that's the way that you can argue on that. So this is a very simple question again. Moving on, the last one of question number 1 is the arrange the following in the increasing order of the properties. So we have done many things like this. So you need to find the melting point order. So here lithium and potassium are the two different elements in the two different periods. So when you compare lithium fluoride and lithium iodide, so you see here lithium is same. So fluorine is on the top of the halogen. So when you go down, fluorine, chlorine, bromine, iodine. So iodine would have a very low electronegativity. And when you compare the difference, then lithium iodide would have a higher lower electronegativity than lithium fluoride. So basically what it happens here is lithium iodide would have the lowest and lithium fluoride will have the next, but Kf, when you come to Kf, it will again very, very small. So it will be Kf here. That's a normal idea. Okay. Then this one is about the stability. So we know there cannot be like a NF5 compound. So it would have the lowest stability. Then out of NO2 minus and NO4 3 you just need to consider what the oxidation state you will see here and the charge. So there are 4 oxygens and 2 oxygen. Most probably NO2 would have the highest stability. In fact, it is because of this oxidation and the charge. So basically NO2 minus is stable than NO4 to NO4 3 okay. Is very, very difficult molecule to form. Again, bond distance. So if you have very fewer bonds, it would have very small length, and when you have more and more bonds, there will be more and more repulsion, and all those things can happen. So basically NOCl, there is a very simple structure. So this should be NOCl, and out of these two, understand, so for an example, if this is like this NO, so there are 3 Cls like this, and the other one is like NO2F. Okay, so fluorine will like pull electrons toward them because it is electronegative, as well as here chlorine as well. But here, remember, there are 3 chlorines that is pulling. There is only 1 fluorine, and there are 2 bonds, oxygen bonds here. So basically, it will have a like a resonance hybrid, which is the length are 2 same in both bonds. But here, 3 chlorines are pulling the electrons. So basically, it would have the highest bond length. Okay, and here it will be NO2F. So this is the idea here.